Hey there folks, Mr. D here, and in this video we're going to discuss conditional probabilities. Conditional probabilities. And whenever we're talking conditional probabilities, there's a phrase, given that. And I know that sounds weird right out the gate, but that's going to be our key word that we're dealing with conditional probabilities. And basically we are finding the probability of something happening, assuming that we're working under a given condition. So it's going to kind of change our probability as we go through. And this will make sense here as we see some examples. First, let's get some vocab and notation covered. So the way conditional probability works is we're finding the probability of a certain event happening, given that another event has already taken place. So this isn't like the whole independent, dependent events where we're multiplying. We're assuming that one condition is already being met, and we're finding the probability of a second one. So here we have probability of B, vertical line A. This is read as probability of B given that A. So B given A. Today when we see these, we're going to primarily deal with contingency tables or just a straight up two-way data table. And that's going to be a nice way to see the totals, and it's going to kind of segment the information easily for us. Later on, we're going to get into tree diagrams and Venn diagrams. So buckle up for those. All right. Probability loves decks of cards, so I've got that there for our reference. Again, tons of these available on a Google image search, or take a picture of the screen if you want. Okay. We have the probability of drawing a club given that we're selecting a black card. So the fact that I'm working under the condition that we are selecting a black card tells me that I no longer need to focus on all 52. I'm only focusing on the black cards. Well, there are 26 black cards in a deck. So this whole given that gives me a stipulation. I'm not worried about all 52 cards. I'm only worried about the 26 black cards. Now, of those 26 black cards, so these 13 here and these 13 here, how many of them are clubs? Well, 13 of them are. So 13 out of the 26 black cards are going to be clubs, which means there is a 1/2 probability. So if I am working under the contingency that I'm selecting a black card, I've got a 1 out of 2 shot of selecting a club. Next up, the probability of selecting a 4, given that we're selecting a black card. Well, just like before, if we're selecting a black card, there's only 26 cards to worry about. Now, out of those 26, so out of the spades and the clubs, out of these 26 cards, how many 4s do I see? Well, I'm only seeing 1, 2. I don't care about these 4s. These 4s are red. So out of only the black cards, I'm counting 1, 2 cards that have a 4 on it. So we would have 2 out of 26. And that, of course, reduces to 1/13. Next up, probability of selecting a diamond, given that the card is black. So out of the 26 black cards, how many of those have a diamond on them? Well, the black cards are either spades or clubs, so there's really no diamonds on there. That'd be 0 out of 26. It's impossible to select a diamond if you're working under the condition that you're only selecting a black card. All right, let's get into some tables here. The table shows student by gender and type of school. In 2005, we pick a student at random. So let's kind of zoom in here. We have males attending 2-year colleges, 4-year colleges, and grad schools. We have females doing the same thing. Whenever you have a contingency table like this, my suggestion to you is always add the totals down at the bottoms of each row and the totals at the end of, bottom of each column, and then at the end of each row, and then get the overall total here. All right, so if I do that, adding straight down 1866, 4324, and 1349, we should get 7,539 as our total. Same thing, next column over, we get 9,933. And all we're doing is just adding straight down. Next, we'll add straight across. If I add straight across here, I'll get 4,328, 9,841, and 3,303. One of the advantages of doing this is if we add these numbers straight across to figure out the total over here, or the numbers straight down, we should get the same value, whether I go left to right or top to bottom. So it's a nice way to kind of double check ourselves to make sure we didn't mess anything up. All right, so now that I have the totals on here, let's get some data. Question 1, what is the probability of selecting a female? There's no condition set on here. Well, if I look at females, there's 9,933 over the total, 17,472. So that probability, and this is going to go straight into our calculators, is the total females over the total people, and that would be around 57%. Next, what is the probability of selecting a female given that they went to graduate school? So I only care about graduate school right here. I only care about graduate school. So this is my only concern. So of those total 3,303, of those total graduate school students, 1,954 of them were female. So anytime we're dealing with that conditional probability, we're kind of narrowing our focus. So it'd be 59%, roughly. Next one, what is the probability that someone went to a 4-year school given that they are male? So if we're operating under the assumption that it is a male, we only care about this column. We're assuming that they are already males. So now we're figuring out what's the probability of 2-year, 4-year grad school, whatever, out of that total of 7,539. Well, of those males, it looks like 4,324 of them went to a 4-year school. So 4,324 up here. Go straight to your calculator. Ooh, that's a weird approximation sign. Ugh. Get about 57%. All right, next one. Utility company asks for 50 of its customers. Well, this is kind of nice. They tell us the total. Nice. So we have 50 total customers. Whether they pay their bills online or by mail, what is the probability that a customer pays the bill online given that the customer is male? So we want probability that they pay online given that is a male customer. With a male customer, that's going to tell us my denominator. I'm not concerned about all 50 people. I'm only concerned about how many males there were. Well, how many males were there? We've got 12 plus 8. There were 20 males. So out of the 20 males that we have, how many of them paid online? That would be 12. So 60%. All right, next one. This one's kind of worked out for us already. Researchers ask shampoo users whether they apply shampoo directly to their head or indirectly using their hand, which, for the record, I don't think I've ever encountered anyone who just squirts shampoo directly onto their head. I feel like I always go into the hand, rub your hands together, lather, rinse, and if you want to, if you got the time, repeat. But that's neither here nor there. What is the probability that a respondent applies shampoo directly to their head, given that the respondent is female? So for this one, we are finding the probability that they're going directly onto the head, given that that person is female. So directly on the head, given that they're female. Well, if we look at the females, there are 30 total. Of those 30, 6 go directly onto the head. Now, if we wanted a set formula for this, and this is essentially what we've been doing all along without formalizing it. If you wanted the probability of B given A, up top you're going to have the probability of both things occurring divided by the probability of the given that statement. So whatever comes after the given that is your denominator. And again, we've been doing that all along without really realizing it. So let's see some examples here. We have a scenario in which a survey was given out to some folks. 39% have a pet now, and they've had a pet in the past. 61% do not have a pet now. 86% have had a pet in the past. 14% they don't have a pet now, and they've never had a pet. Now, if I added all these percentages, I'd definitely get more than 100. So there's clearly some overlap going on right now, right? Because of these 86% that have had a pet, there's 39 of them that still have a pet now. Same thing, of these 61 who don't have a pet, some of them have never had a pet. So there's definitely going to be some overlap here. First one, find the probability that a respondent has a pet given that the respondent has had. All right, so I want the probability that they have a pet now, given that they had a pet in the past. So what is the probability they have a pet now, given that they've had a pet in the past? So I need to know how many of them have had a pet previously, and that would be that 86%. Now, you could write that as 0.86, but as long as I'm consistent with my decimals, whatever I do up top and bottom, I don't need to worry about it, so I'm just going to leave that as an 86. Now, of the people that have had a pet, how many of them currently have a pet? So in the top, it's going to be the probability of someone having a pet who also had a pet. And that was at 39%. I go to my calculator, I divide that out, we'll get about 45%. That is the probability of randomly selecting a person who currently has a pet, given that they've had a pet in the past. Next one, find the probability that a respondent has never had a pet, given that, so we have probability of never had a pet, given that they don't have a pet now. So I'm going to use the phrase that comes after my given that to get my new denominator. So what percentage of people do not have a pet now? That would be 61%. Now, of that 61%, I want to know what is the probability that I select someone who's never had a pet and they currently don't have a pet. So they don't have one, they've never had one. And that is 14%. So I've got 14 over 61. That's going to give me 23% overall. All right, last and final problem. Here we have a contingency table of job applicants. So applicants might or might not have work experience. They might or might not have a high school diploma. One thing that is not given to me on this table, nor is it given in the prompt, is my totals. So I'm going to take a moment here to go through and calculate those. So I'll add up straight down at the bottom of each column. I'll do so at the end of each row. And I should get the same total, oopsies, in that bottom corner. So 90 both times, cool. So if I want the probability that someone has a diploma, so 81 people do have a diploma out of the 90 total, we'd have 81 over 90. Go to your calculator, you'll get 90%. I want the probability that someone has both a diploma and experience. So they have a diploma and also experience. So there are 54 people that meet that criteria. So 54 out of the 90, 60%. Next, the probability that they have experience given that they have a diploma. So again, this given that statement means I'm no longer dealing with all 90. I'm only dealing with the diploma folks. So those 81. So out of those 81 diploma people, how many of them have experience? Well, 54 out of the 81 have experience. So 54 out of 81, about 67%, 2/3. Next one, they have no diploma, so they do not have a diploma, given that they have experience. So for this one, I'm only worried about the people who have experience. So the people who have experience, there are 59 of those folks. Of those 59, 5 of them do not have a high school diploma. Okay? Of the 59 people who have experience, 5 of them do not have a diploma. So we're going to have 5 out of 59. We go to our calculator, we get about 8%. All right, that is it so far for conditional probabilities. Down the road, we will get further in depth with both tree diagrams and Venn diagrams, and that should lead us towards the end of Unit 7. You know the drill, folks. If at any point you're stuck, please let me know. And as always, good luck, have fun, be safe, roll tide.